So welcome back to lecture number 2. In the first session, we saw that AI is being deployed in railways right now in maintenance, in safety, and in operations. We also identified a fundamental challenge that AI introduces new uncertainties and failure modes that traditional softwares did not face. But we also made a crucial claim that the existing standards, for example, 50126, 128, and 129, they still do apply and are sufficient to assure AI if applied rigorously. In this lecture, we are going to dive deep into those standards and show you exactly how to apply them to AI systems. You will learn 4 things. First one, we'll discuss what RAM means and why it's the framework for all railway assurance. Secondly, we'll discuss how 50126 defines the life cycle and hazard assessment process. Then third, we'll discuss how EN 50716 specifies software development, including for AIs. And towards the end, we'll discuss how EN 50129 structures a safety case and technical safety report for AI containing systems. So by the end of this session, you will have a mental model of how these standards interconnect and how to apply them to any AI systems you encounter in railways. So let's talk about RAMS. So RAMS stands for reliability, availability, maintainability, and safety. These are 4 interconnected dimensions of railway system performance, and they are the organizing principle for everything we do in railway assurance. So let me define each one by one. First, reliability. So by definition, the reliability is the probability that a system performs its intended function for a specific time under specific condition without failure. So in practical terms, a highly reliable train fleet breaks down less often. That means fewer breakdown means fewer disruptions, safer operations, and better passenger services. Secondly, availability. So by definition, availability is the proportion of time the system is operational. In other words, uptime. If a railway has 95% availability, it's operational 95% of the time and down for maintenance or repair for 5% of the time. High availability means more trains are running, generating more revenue, and also the better service. And then third is maintainability. So by definition, maintainability is how easy a system can be restored to service after a failure. If your crew can diagnose and fix a fault quickly, the system is back in service fast. Maintainability is related to diagnostic clarity, repair accessibility, and spare parts availability. And fourth is safety. By definition, the safety is the absence of unmitigated hazards. A safe system will not cause harm. In railways, safety is the paramount. Is the constant that all other decisions must respect. Now, here's the key point. These aren't separate concerns. They are all integrated. RAMS, they are all integrated. If you maximize reliability without proper maintenance, you are setting yourself up for sudden catastrophic failures, which are dangerous, and it will also disrupt availability. So if you minimize maintenance to maximize availability, you are allowing degradation to accumulate, which erodes both reliability and safety. So overall, RAMS is a balanced integrated approach, and EN 50126 provides the process to manage this trade-off. So let me walk through how AI affects each RAMS pillar. Let's start with reliability first. So the upside is that AI-powered condition monitoring can now detect subtle degradation in the components, may it be bearing vibration or wheel geometry changes or catenary wear and tear. The AI-powered condition monitoring can detect those critical degradations weeks or months before the critical threshold. So this allows planned maintenance before the failure. So that means fewer unexpected service failures. As a result, it will increase the reliability. So the result will be the higher reliability. But there's a downside to it, and that's a critical one for the assurance. First one is that the AI introduces new failure modes that are different from the traditional hardware failures. So if an AI model misclassifies the condition as a condition of a component as, let's say, it says that it's healthy, and when it's actually degrading, then maintenance team misses the problem. The component will fail unexpectedly. This is a systematic failure. The AI system consistently makes the decisions which are wrong in certain scenarios. Similarly, if the training data is unrepresentative, says it's biased towards only one route or one type of trains or one type of climate, the model performs well on that data, but when it's deployed somewhere else on a different climate or a different project or using a different rolling stock, it will perform poorly. The same model will fail over there. So this is a data quality failure. And if the model drifts over time, its accuracy gradually degrades as the real world condition shifts. What's the assurance implications here? You cannot just trust that an AI model will reliably detect failures. You must validate it on its representative data, identify the conditions where it degrades, and monitor its performance in operations. So if accuracy drops, you stop there, you stop training your model, and then you return or you roll back to the earlier model version. Okay, just like reliability, next we'll discuss availability. Availability is about uptime, so which AI can significantly improve it, but it also introduces new risk. Same as what we discussed in reliability. It will significantly improve availability, but new risks will be introduced. So what are the positive sides? Among the positive sides, we have predictive maintenance, which is now relying on AI-based condition monitoring. That means that you intervene before the failure. That will reduce the unplanned downtime and emergency detachments. So the continuous AI monitoring system will detect the issues faster than it's detecting during the schedule inspections. So optimized scheduling means you do maintenance during planned possessions, not during the revenue generating hours. So as a result, we'll get higher availability. That means more trains are running and more revenue is being generated. But then there's a negative side to it. If an AI services itself becomes unavailable, the model will crash, the system goes down, and that's a network outage. What will happen then? If there is no good fallback system to switch back to the traditional inspection or operations, the availability will collapse. This is a single point of failure risk that must be mitigated through redundancy or graceful degradation. Also, if the AI system overpredicts failure, means there are a lot of false positives. Maintenance teams are constantly pulling components for inspections only to find out that there's nothing wrong with it. That increases the downtime and frustrations. So staff will start to distrust the AI system eventually. And over the period of time, if false positive signals are increased, staff will start ignoring the recommendation and they will eventually just disable the system. And if you update an AI model frequently without proper testing, regressions are likely to happen. So what are the assurance implications here? For the assurance implications, we have to design the system that will degrade gracefully if the AI becomes unavailable. We should always validate the model updates. Don't just implement the AI right away. We have to do a proper validation so the system doesn't introduce regressions. We have to always monitor the false positive rates alongside accuracy. If they spike, investigate why they are spiking, and if it's needed, we always have to retrain the model. So next is maintainability. Maintainability is about how quickly and easily you can fix something that breaks. So positive sides of implementing AI in our maintenance regime is if an AI system tells a maintenance technician exactly which bearing is degrading and by how much, the technicians can quickly locate it and replace it. There is no guesswork needed. So AI-driven diagnostics will always accelerate troubleshooting, and also predictive systems will prioritize the work. It can tell technicians which bearing to address first and which one to address second. It can just assign the priority to that. So it is using this predictive maintenance system, you can allocate the resources efficiently. But the negative side of it is if an AI system flags a problem but cannot explain why. In this case, maintainers only have two options: either trust it and spend time verifying it, or distrust it and ignore it. Neither is ideal condition. So in this case, trust will erode and efficiency will drop. So complex AI models, especially deep neural networks with millions of parameters, it's very hard to debug. If a model takes a wrong decision, how do you figure out why? With traditional softwares, you step through code. You can debug the code and check and find out exactly where the code is giving us error. But with neural networks, there is no clear logical path to trace. And AI system depends on data pipeline. If sensor data stops flowing, if processing fails, and if the data quality degrades, the AI's outcome will become unreliable. A maintainer might rely on an AI recommendation, but that's based on corrupted data. So, what are the assurance implications here? For assurance implications, we have to prioritize explainability and transparency. We always have to use tools that helps analysts understand AI decisions. We have to implement data quality monitoring and always plan for model updates and retraining as a standard operational procedures. Document the model's limitation and conditions under which it degrades. Okay, let's move on to safety. As we discussed earlier, that safety is the paramount in railways. And AI introduces the most significant assurance challenges here. The positive side is, if we implement AI, it can help us save lives by detecting the hazards earlier. For example, an AI vision systems can spot obstacles at level crossing before humans would. Another example is automated incident analytics. That system can surface the emerging safety risk much earlier as compared to manually reviewing our incidents. Now let's discuss something that keeps safety engineers awake at night, the critical challenges. So currently there are 4 critical challenges that we are facing implementing AI in railways, and that's impacting safety. First one is the model uncertainty. The AI model might output 95% confidence this is a critical rail crack, but there is still a 5% chances that it could be wrong. For safety critical decisions, is 95% good enough? How do you set the decision threshold? If you set it too low, you get false positive and waste your resources. If you set it too high, you miss the real hazards. This is the quantitative safety assurance problem that requires careful analysis. Second challenge we have is adversarial example and edge cases. AI models can be fooled by unusual inputs that they haven't seen in training. A vision system that is trained on RGB images might fail when faced with reflections or shadows or unusual weather. A model which is trained on a standard gauge track might misidentify broad gauge defects. Thirdly, systematic failures from biased data. So if the training data overrepresents one type of failures and underrepresents other type of failures, the model will miss the underrepresentative failure modes. This is insidious because it's not a random failure. It's a systematic, predictable blind spot that you must discover and address in the safety case. Fourth challenge we have is the human-AI miscommunication. If an operator don't understand the AI's limitation, they might overtrust it or they might misuse it. That means they're relying on it in condition outside this design. So what are the assurance implications? AI must be explicitly modeled as a safety relevant component when you are doing hazard analysis and risk analysis. So AI must be modeled as a safety relevant component. You must identify AI specific hazards. You must always validate the model on its diverse representative data and also include the edge cases and scenario variations. And you must define the operational design domain, ODD. It's a very important term. We'll be discussing about it further on in our session. So you must always design a very crystal clear operational design domain, because later you will design a monitoring system that will detect when the system is operating outside its operational design domain, ODD. And lastly, you have to design the operator interface to prevent misuse and support proper mental models for AI capabilities. So here's a crucial insight. RAMS is integrated, means you cannot optimize one pillar without affecting the others. If we apply our traditional engineering approach, we get few suggestions. First one is to maximize reliability by using the most robust fail-proof components. That is one way to improve the reliability. But that means we'll have to do more maintenance, and as a result, that will reduce availability. That's one option. Second option is, okay, let's maximize availability by minimizing the maintenance. But that will let degradation accumulate. As a result, the reliability will be reduced and we'll have more safety risks. In railways, safety is the overriding constraint. All RAMS decisions must respect safety. Within that constraint, you have to balance reliability, availability, and maintainability. Okay, let's just discuss a scenario here. For example, you discover that the wheelset wheels are failing faster than expected. You are given 3 options. Option A is to increase inspection frequencies. As a result, we'll have more maintenance and the availability will be low. But in this option, we will catch more failures much earlier. Option B is to replace wheels more frequently based on the preventive schedule. It will be a simple maintenance, but that's less efficient. And then on option 3 comes in. We deploy AI predictive maintenance. Using this AI predictive maintenance, we catch failures much earlier without increasing the inspection burdens. As a result, availability and reliability both will be improved. CENELEC standard EN 50126 provides the structured approach to make this trade-off decision rationally and safely. That's what the RAMS cycle is. So, CENELEC standard EN 50126, it's a RAMS lifecycle standard. It's the foundation of everything we do in rail assurance. Okay. So this standard defines 10 life cycle phases, starting from concept and all the way up to decommissioning. So each phase has specific activities and decision gates. All right. So crucially, 50126 is not perspective about models or tools. It doesn't say use this analysis technique or use this test frame. Instead, it just defines what must be done at each phase, right? So what evidence must be gathered and what decisions must be made and what risks must be what kind of risks must be managed. Okay, so this flexibility is powerful. It allows different organizations to implement EN 50126 using their preferred tools and processes as long as they meet the standards requirement. So the life cycle is also iterative. As you progress through phases, you gain more information. You might discover new hazards and refine risk assessments. So you loop back to earlier phase to incorporate those new understandings. Okay. So this iterative approach is especially suited for AI projects. In AI projects, that's why I'm saying it's especially suited for AI projects, because AI projects is where where the uncertainties are high and the learning happens through validation and operation on each phase of the project. So that's why when I say that this iterative approach is especially suited for AI project, that's what I mean. Let's walk through the phases first. So first phase in our life cycle is concept and feasibility. This phase is where you define the system needs and business case. For example, a railway operator might say that we have too many unexpected wheel failures. This disturbs the service and it creates the safety risk. We need a solution. And the candidate solutions might include option 1, like how can we solve this issue? We can either do more frequent wheel inspections, either we can do more aggressive preventive wheel replacements, or we can do the AI predictive maintenance using existing wild data, wheel impact load detector data. So if we are going to use more frequent manual wheel inspection, it's going to be higher labor cost. If we're going to do preventive wheel replacement, it's going to be higher material cost and more downtime. So middle ground is we are going to use AI predictive maintenance using existing wild data. So in phase 1, you explore these options. You gather the input from all your stakeholders. When I say stakeholder, it's the operations, maintenance, engineering, all of them. And then you decide which direction to pursue. You also identify your preliminary constraints like budget, timeline, and then regulatory environment. So for an AI project, a key phase 1 decision is, what will AI do? Will it be advisory? Will it be supportive? Or will it be system safety critical? So if it's advisory, that means the system suggests the wheel might be degrading and operators decide. So the purpose of AI model is only to give you an advice. Second is supportive. If the role is the supportive for AI, system will detect the degradation of the wheel and suggest schedule maintenance, and operator can always override. Operator still has the end option to override the suggestions given by the AI. And third is the safety critical. So if the role of the AI is safety critical, that means the system directly drives the safety related actions. For example, whenever it sees the degradation in the wheel, using the wild data, system automatically reduce the speed. Obstacle is detected, system will automatically reduce the speed. So this is the safety critical system. So this choice affects the assurance for the system overall. This was about the phase 1. And in phase 2, we discuss about the system design. So phase 2 is where you develop the high level architecture and then allocate RAMS target for a subsystem. Architecture may look like, for example, for wheel degradation detection, architecture might be like trackside wheel sensor will pass on the data to the data collection system. Data collection system will further pass on the information to AI model, which will feed it to its neural network and then gather information and look for the patterns, and then pass on. AI model will further pass on the data to MMS, maintenance management system, and then from a maintenance management system, the request will be forwarded to depot technician. So from the wild sensor to depot technician, this is a whole journey in how the data will be passed on. So in this phase, we will also assign the RAMS target. For example, we can assign a target like this system must identify degrading wheels with 95% and above reliability and less than 2% of false positive rate. So we have to define the sensitivity and specificity of this RAM target of the system. So for AI, phase 2 is where you design the AI subsystems. You have to decide, okay, what inputs will it choose? What outputs will it produce? What's its fallback behavior? Because remember, we have to design the system which will degrade gracefully, right? So we have to decide what is the fallback behavior. Critically, you define the operation design domain, as I mentioned that word in the previous slide as well. So we define the ODD. In the ODD, we have to decide about the quality of data when it's being trained. That, for example, this model is trained to predict wheel failures in UK's standard gauge railways with standard train fleets in a typical UK environment. So this kind of RAM target, this kind of information will be part of the RAMS target in part of the AI subsystem in phase 2. So then we move to phase 3. Phase 3 is about the detailed design. So in this phase, you're going to specify the AI models in detail. Okay, so you will decide like what type of model you are going to use. Is it going to be a neural network? Is it going to be a random forest? Or it's going to be a simple statistical model? And also you will decide like which features will you use, and what will be the what will be the requirement of data, what will be the requirement of the quality of data, and how will errors be handled. So for example, for wheel degradation detection system, you might specify that the model you will use will be you're going to use gradient boosted tree model, XGBoost, with inputs like wild shock magnitude, your bearing temperature, your wheel age, and the kilometer traveled since last turn. And then for the training data, you might specify something like you want to use outcomes of 10,000 wheels over the past 5 years, operational data of 10,000 wheels over the past 5 years, and their results, their outcomes, like did they fail or not failed. And then for the data quality, you will be deciding that something like missing values should always be less than 5%, and outliers should be flagged and handled. And then what will be your fallback model? So if the model will fail, what will be the confidence level? So if the model fails, model confidence level is 0.8, is less than 5.8, what will be the flag? Is it going to fall back to another AI model, or will it be fall back to, or should it be flagged as a manual inspection? So what will be the confidence level on this AI system? So this is about phase 3. Phase 4 is about implementation. This is where you're going to build the system. You're going to train the model on prepared data. You're going to implement monitoring to track model performance, and then you set up version control, Git version control for training code. So you're going to set up version control for training code, and then you serialize the model for standard format, and then you implement the data pipeline. This is all the part of phase 4. This is where what we say when the rubber meets the ground. This is the phase. Then next one will be the phase 5. Phase 5 will be about validation and testing. So in phase 5 is where it's where you do the comprehensive testing to ensure the system works in the real environment. So you're going to test the AI models on a handheld test data. Like for the wheels which are not being used for training, you're going to use that side of those wheels, and then you will measure the metrics, the results like the accuracy, specificity, sensitivity, and false positive rate. And then you're going to conduct operational trial where you will deploy a real depot. You will deploy the system to a real depot for 10 to 12 weeks or 10 to 15 weeks. And then you're going to track all predictions and outcome. You're going to measure the real world accuracy. Then you're going to collect the feedback from the maintainers, where you will talk to the rolling stock team and you will understand their recommendation, and you will ask them if they trust the system and if they frequently override the system. So all this information you will gather back from your maintainer, and then if the validation results are positive, you proceed to the deployment. If it's not positive, that means you reiterate, because this is how the life cycle works, right? So if it's not, the validation results are not positive, you refine the model, you gather more data, and then you adjust the thresholds accordingly. Okay, the next one we have is phase 6, that is deployment. So deployment is where you roll out the systems to operations, and then you will install the hardware, your software, install the software. You're gonna train the staff, and then you gradually ramp up, where you might start with one depot first and then expand to other. So this will allow you to catch deployment issues without disrupting the entire network. This is what happens in the deployment phase. And then next is the phase 7, that is operation phase. This is where the system runs in production and serves its purpose. So this phase is so crucial because this is where you monitor the system. It's very critical to monitor the system. Like in a traditional system, for example, fixed signaling installation, once the system is deployed, the behavior is static. But for AI system, the behavior can change as the system can drift when it gets the input from the real world condition. So as the real world condition will change, the model performance may degrade. So you must always monitor accuracy metrics weekly, monthly, and then you can decide the frequency when you want to measure. Then you should always track the false positive and false negative rates of the model, and you should always detect if the system encounters condition outside its ODD. And what will happen if the system encounters the condition when it's not within its ODD? What should be the acceptable threshold? And if the system has encountered the condition outside ODD, what's going to be trigger? Trigger should be for retraining the model or you roll back. So this is what you'll be discussing and you'll be implementing in this phase. This is not optional. This is all part of the safety case 50128, which is upgraded to 50716, this standard explicitly requires continuous monitoring and model governance. So for operational AI systems, this is requirement for the standard 50716. Next is phase 8, which is about the maintenance and support, which involves fixing the bugs, you update the models, and then extending system's lifespan. Any model update is a configuration change and should go through the change control process within the organization. So you will assess the impact, you will test the new model, you will always validate on a real world data, and then you will monitor when it's in operation. And then next is phase 9, that is modification and evaluation. This is where you make the major changes. If you want to add new features, you want to support the new rolling stock, or you want to extend the new routes, this is going to be handled in phase 9, modification and evaluation. And also, I want to mention that major changes are treated as new deployment. So if there is a major change happening in the system, you go back to your hazard analysis and risk analysis, HARA, and then you redefine the requirements, and then you have to revalidate again. The whole system should be revalidated again. So this prevents the death by 1,000 small changes, where small updates gradually degrades the safety without even noticing. So to avoid that, we always have to go through the initial process of hazard analysis and risk analysis, and then validation again. Next phase is phase 10, which is about decommissioning, is where you retire the system. Once the system has completed its lifespan, transition to the legacy or replacement system, and then you will archive all historical data and model versions, and document all the lesson learned. And this knowledge can be used as an input for the future projects. Okay, these are all the phases of the life cycle. So within each phase of 50126, there is a hazard analysis and risk analysis cycle as well. So in short, it's called HARA cycle, hazard analysis and risk analysis. Hazard analysis and risk assessment cycle, where the step 1 is to identify the risk, where you can you have to decide like what can go wrong with the system. Like for AI, this includes like AI misclassifies a component state, our AI model drifts, our AI system becomes unavailable, or maybe the operator will misunderstand AI output and make the wrong decision, like that, etc. So these are the identified hazards for the AI systems. Step 2 will be about the assessment of the risk, where you will assess each hazards and then you estimate their severity, their frequency, and their controllability. So in severity, you will discuss like what's the consequence if the hazard manifests. Is it negligible, minor, serious, or catastrophic? And in frequency, you will discuss about how likely it is going to happen. Is it rare, low, medium, or high? And controllability is like, can the operator detect and intervene? Well, the options are like usually yes, sometimes, or rarely. So product of these three factors will become the risk. So risk will become like a severity times frequency times controllability. So in other words, for the high risk, we can define something like catastrophic consequence happening rarely but uncontrollably. It's a high risk for us. So step 3 will be about define control. Like how do we reduce the risk? Some options, generally speaking, some options are design change, where you can redesign the system to eliminate the hazard. Protective equipment, where you can add redundancy, like fallback, monitoring systems, or you can include some procedures where you define operating procedures that avoids the hazard. And then you can educate your staff as well, like how to handle the edge cases. So for AI model misclassifies this kind of hazard, what should be the control that must be included? Design change can be something like you validate the model on diverse data. That's like a design change. Then you implement the confidence threshold. If it's below threshold, you flag it for the human review. That can be something like protective equipment. And then you have to train the maintainer to spot the false positive, and then they have to report them. That's like a procedure. So that's the step 3 of hazard analysis and risk assessment. Step 4 of the hazard analysis and risk assessment cycle is verify control, where you will test or analyze that the control works. So does the confidence threshold mechanism actually prevents false positive harm, or does the maintainer training actually improves their reporting? This is what you're going to check and verify in the step 6 of hazard analysis risk assessment cycle. Next step is documentation. So for each hazard, you have to do the risk assessment. You have to write in their controls, and then you have to document their verification. So all this information, all these records will become part of your hazard log, and this hazard log is being fed to the safety case, which we'll be discussing when we'll discuss about the standard CENELEC standard 50129. So critically, the system is iterative. So as you learn more through design, testing, or operation, as you learn more about the system, you refine hazard assessment. And then you might discover a new hazard in phase 5 that you did not anticipate in phase 2. So if you discover a new hazard, you loop back, you assess it, you define the control, and then verify it again. So this iterative risk-driven approach is perfect for AI, because in AI systems, the uncertainties are high. You cannot anticipate all failure modes upfront. So instead, you manage a rolling set of known risks and continuously search for the new ones. Okay, let me walk you through some concrete example of applying 50126 to an AI system. So hazard we are going to discuss here is that the AI model fails to detect wheel degradation. A wheel that is actually degrading is classified as healthy by this AI systems. This is just an example. So in our risk assessment, we will define severity, frequency, and controllability. So severity we can define as we can set as a catastrophic, because we know that undetected wheel defect can cause a derailment, and in the result it can result into fatalities. So severity is catastrophic. Frequency really depends on the model quality. If the model is 95% sensitive, that means it catches 95% of degradation, then around 5% of truly degrading wheels will slip through undetected. So if there are 100 degrading wheels per year, That means 5 wheels per year that are missed. So frequency really depends on the model's quality, and controllability is, I think, is low because the controllability is low because maintainers rely on AI systems. They cannot usually spot a degrading wheel visually. So that's why we are using AI system here to detect the degrading wheel. So a result here is high risk hazard. So we are going to apply some controls to to mitigate this risk. First one will be to validate the model thoroughly. So we have to train the model on, let's say, 10 years of wild data, and then we are going to train the model not only for 10 years of wild data, but we are going to test the wheels from different supplier in a different climate using different train type, and then we are going to achieve 95% and above sensitivity before the deployment. Second control we can apply here is to monitor accuracy in operation. So we're going to track true positives and false negatives. So if false negative rates creeps above 5%, we have to investigate and retrain the model. Third control measure we can apply here is to implement a fallback. So we have to retain a secondary inspection mechanism. For example, every wheel still goes through visual inspection at major depots annually or every 6 months. So this catches any wheel that AI is missing. Fourth control measure we can apply here is to define our out of ODD handling. If a system encounters a wheel that it was not trained on, or it was on a different climate that it hasn't seen, flag it as a manual review rather than blindly applying the model. These controls reduce risk to acceptable levels. The risk is not zero. It's always possible for a degrading wheel to slip through, but with multiple layers, models, accuracy, monitoring, ODD awareness, and fallback inspection, the residual risk is acceptable. EN5012 and its modern update, that is EN50716, it specifies a software development lifecycle for all softwares that contributes to safety function in railway systems. So the standard defines 6 main processes area for software development lifecycle, 6 main process areas. First one is requirement, second one is design, third is implementation, fourth is verification, fifth is validation, sixth is configuration and management. So let's dive deep into these phases one by one, these processes. First one is requirement, where we have to set up like all the requirements for the software that must be traced from the system level safety requirements, that is from 50126 hazard analysis and risk assessment. And all the requirements should be clear and testable. The model must detect rail cracks. For example, the model must detect the rail cracks with 95% and above sensitivity. And the requirements must be unambiguous. Like it should specify exactly what should be the input, what should be the output, and the performance metrics. So for AI, let's have like example requirement specification. For AI model, specification could be like model accuracy targets, where we have to define the targets for like sensitivity, specificity, or false positive rates. Then we have to define data requirements about the quantity of data, diversity of data, and quality of data. And then operational constraint, that is, we have to set up the ODD. And then we have to have a fallback behavior of the systems. All these should be listed in the requirements for the software, which is the first process of SDLC, software development lifecycle. Second process is its design, where you specify the structure, the standard software architecture, like how is the AI model integrated with the surrounding systems. You will answer the question like what are the data pipelines and what are the error handling procedures. Third process area is implementation, where you will actually write the code. You will train the AI model. You will implement data pipelines, pre-processing and post-processing, and you will write the supporting softwares like for monitoring or logging errors or fallback logics. You will design those. And also you will use like a version control for version control and like standard coding standards. You will be following that. Fourth process area is the verification, where you will test the product test that the product actually meets the specification, like does the model actually achieves the 95% and above sensitivity on test data or not. You will check like do the data pipelines correctly handle the missing values, or you will check like do the error handling paths work as designed. So these are all questions that you will be answering during the verification stage of the software development lifecycle. Next phase will be the validation. In the validation part, you will test product will actually solve the real world problem. You will check that does the model works on the real operational data, like do the maintainers find it useful or trustworthy. You will check does it actually prevent the safety hazard you intended, or is it not working as it was required. Then sixth phase will be the configuration and management, where you will have the control versions and its changes. You will maintain the version control for the code. You will track all data variations. You will track all model versions. Any update to the model, there should be a process of a change control process that you should be applying any update to the model. So these are the 6 phases which are part of software development lifecycle, which is discussed in EN standard EN 50128. Also, let me just quickly give you an overview about the software integrity level. The rigor requires depend on the software SIL. That is like a measure of how critical the software is to safety. So we have 5 standard measures: SIL 0, SIL 1, SIL 2, SIL 3, and SIL 4. SIL 0 is like no safety requirements, like minimal process. SIL 1 is basic assurance and standard practices. SIL 2 is we need medium assurance and formal methods may be used. And SIL 3 is where we need high assurance, like you need formal verification, validation, and exhaustive testing before deploying the software. Then SIL 4 is the maximum level of assurance, where all techniques are applied. For wheel degradation AI system, where the hazard can lead to derailment and it can be catastrophic, software SIL will likely be SIL 4 or SIL 3. It will be requiring rigorous verification and validation, comprehensive document, and careful management of all the changes. Okay, let me walk through how EN 50126 applies to wheel degradation AI systems. So our first phase was requirement phase. So requirement can be something like a model must predict wheel degradation within 7 days of critical threshold with 95% sensitivity and less than 2% of false positive rates. So we can include something like a wheel has to be from suppliers ABC using wild and temperature data on standard gauge UK railways. So we have defined the specific requirements. So if we read out this statement, so these requirements are specific, they are testable, and they are traceable to the hazard. Because in the hazard section, we discussed as an example hazard as like AI misses the wheel degradation. So it's related to that. Second phase is the design phase. In the design phase, we will be using a gradient boosted tree model. That's an AI model, XGBoost model. And we'll be training it on a historical wild and temperature data. For an input, we will be using wild shock magnitudes for last 1000 wheels rotation. We'll be using data like mean bearing temperature for the last 7 days, and then we will also input the wheel age, or we can also input the wheel kilometer the wheel has traveled. For the output, we'll be expecting system to give us an output in terms of probability of degradation, that is between value from 0 to 1. So we will categorize it between 0 to 1. If the probability is greater than 0.8, we will flag it for the maintenance review. If the probability is between 0.5 to 0.8, then we will add it to the watch list. And if the probability is less than 0.5, no action has to be taken. Means that that wheel is healthy. No need to worry about that wheel. So this design specifies the model type, input, output, and decision thresholds. Next phase is the implementation phase. In the implementation phase, we will be coding the data pipeline in Python. We will design a system that can read the CSV files from the file server and then interpolate missing values, normalizing and the input, and output result has to be passed to maintenance management database, MMS database. We will also be having implementation for a software that can log the errors and also log the predictions. We are going to be using Git for all the version control. Next phase is the verification phase. The verification phase is when we will be checking the product meets its specification. For the verification phase, we will train the model on, let's say, 10,000 historical wheels, and then we will validate on 1,000 held out test wheels, and we will measure its sensitivity for the true positive rate. We will be expecting the result to always be above 95%. And also we will also be measuring false positive rate on the healthy wheels, and we will expect the result to be less than 2%. If not met, we have to retrain the model with the different features or different parameters of the wheel. And then we will be documenting all these test results. Next phase is the validation phase. In the validation phase, we will be testing the system on the real operations. We will deploy a system on Depot A for 12 to 15 weeks trial period. We will compare AI prediction to actual wheel outcome and then measure real world sensitivity and false positivity rate. We will be collecting the feedback from the Depot team on usability and the trust of this system. Also, if the real world performance meets the test performance and maintainers are confident, we will be proceeding with the wider deployment. So this methodical approach ensures that the AI system is built rigorously and validated comprehensively. Okay, next we'll discuss about our CENELEC standard EN 50129, and that is about safety case and SIL assessment. So EN 50129 defines the structure and content of safety case. The document that is called an argument document, and that the system is acceptably safe. So a safety case is not just a document, it's a logical argument. So argument will follow this structure. It has 8 sections that includes context, safety claims, hazard analysis, risk controls, evidence, then assurance argument, then restrictions, and then towards the end there's a conclusion. So each section I will just quickly at 1 to 2 lines. So in the context, we'll describe the system clearly. Like in our example, if we carry on the same example, we have to write something like, we will mention that we have a wheel degradation detection system deployed in, for example, UK depots. In safety claims, we have to state that what we are claiming. So as per this project, implementation of AI in the wheel detection system, we can mention something like that this system reduces derailment risk from wheel defects to an acceptable level through early detection and intervention. So that can be our safety claim. Third section will be hazard analysis. In this part, we will summarize the hazard from practice when we were working on hazard analysis and risk assessment. So that hazard should be summarized here. So primary hazard is that an AI model will misclassify the wheel's condition. I mean, it's going to show healthy, but in fact the wheel is degrading. So that allows the degradation to progress undetected. So that's our hazard analysis. Next section of the safety case is the risk control. In this section, we'll just describe how do we mitigate the hazards. Previously, we have discussed 4 options which we were using to mitigate this kind of hazard. First one was the rigorous model validation, where we have to show that the sensitivity level is always 95% and above on the test data. That was our option number 1, first step. Second, option B, the second step was continuous monitoring of the system when it's in operation. Third one was continuous wheel inspection. That will be a fallback method. If the system fails, the manual wheel inspection will still be in place. Then option 4 will be, the fourth control was, we have to do the clear definition of the model where the model is valid. Like we have to clearly define the ODD. Next section is our evidence section of the report of the safety case. In evidence, we have to cite the evidence supporting each control. Like we have done testing of the system in the depot. We have to mention that what the actual result that we achieved. So we have to say something like a model validation report shows that 98% sensitivity of 1000 wheel set was observed, and 96% was the sensitivity level shown by the system while it was in operational trial over 12 to 15 weeks. So, and also the survey from the maintainers are showing 85% and above as a trust level as per their recommendation. The next section of our safety case is assurance argument. So we'll connect our evidence to our claims. So it will be something like, given that the model achieves 95% and above sensitivity in both test and operational settings, and the maintainers have confirmed that the system is usable and is trustworthy, and that the manual inspection remains as a fallback, we argue that the primary hazard is controlled and is in acceptable level. Seventh section is our restriction. What is the restriction for this implementing this kind of system? We have to state the limitations. Like, this safety case is valid only for UK standard gauge railways for the freight application using wild data from wheels supplied by the manufacturers of, for example, A, B, C. You have to specify which manufacturer's wheels were used. And then if deployed in a different gauge or in a different supplier and are in a different region, the validation process has to be done. It has to be. Eighth and the last section of the report is the conclusion. That's where we have to mention something like this. You have to state that whether the system is safe to operate. You can say something like subject to the restrictions above and continued monitoring of model preference, the system is safe to operate. So these are the 8 sections of the safety cases. Quickly about the SIL assessment. So EN 50129 also requires us to do the SIL assignment for the system. So like we have to mention that how critical is this system to safety. Earlier we were discussing the risk metrics where we have discussed about the severity, frequency and controllability. So for wheel degradation system, severity we can say is catastrophic. So we'll categorize the severity as the catastrophic. For the frequency is very low and controllability is rarely. So in this case, SIL 3 is appropriate because it requires a higher assurance from us and it needs comprehensive evidence. Okay, after safety case, let's discuss about the technical safety report. I'll be referring it as TSR. So TSR is the document that collects all evidence and details that supports the safety case, okay? So like it's a proof backing the safety argument. So for an AI system, the comprehensive TSR will include 8 sections. First section will be the system description, then hazard analysis, then design specification, then our validation and verification results, then ODD definitions, then monitoring plan, restrictions, and then configuration control. Let's quickly discuss briefly one by one. First section is safety description. So this is where we will have the overview of the system, about its architecture, about its components. For example, description of our project, our system can be like, the wheel degradation AI system comprises of trackside wild sensor, data collection and pre-processing, and XGBoost model, the AI model we are using, and a monitoring dashboard and integration with the maintenance management system. This all information will be part of system description. Next section is the hazard analysis. So hazard analysis will include the hazard log and the risk assessment that we have done covering the EN 50126 standard. And we have identified 4 major hazards in this system. First one was AI model will misclassify wheel state. Second hazard was that model will drift in operations. Third hazard we have identified was the operator will misinterpret the AI output. And fourth hazard that we identified was that the system will become unavailable. System unavailability was the fourth hazard. So we have to also include all the risk ratings and mitigations for each. Third section of our TSR is the design specification. Here you will include all the technical details about the AI model. You have to include the details like which AI model are you using. Like in our example, we are using gradient boosted tree, XGBoost. You have to include the version number as well. For example, if you are using XGBoost version 1.5 or 1.6 or 1.7, you have to include that. So you have to include in this section the model types, all the inputs. Which inputs are you getting from the wild? You are getting the wild shock magnitude, bearing temperature, wheel age. Also, what are you expecting as an output? Output will be the degradation probability. So result will be in the probability between 0 to 1. And what training data sets are you using? How many wheels are you using? So in our example, we have used 10,000 wheels data for the past 10 years. So these details will go into the design specification. So next section of TSR is VNV results, or verification and validation results. That report will include our information like our verification, that model validation on our 1000 wheel set, where during the testing phase, we were able to find the sensitivity level was 98%, specificity was 99%, and false positive was 1.2%. That was the result of our verification. And then the results of our validation as well, where we have to check into the operation trial phase. So we have to include the results in our operational trial phase, that at Depot A for 12 weeks when the system was tested, the real world sensitivity was 96%, false positive rate was 1.5%, and from the maintenance survey, we received the results like 85% were having the trust, 12% of the time it was the decision was manually overridden, and 3% was distrust. These are the details. The results will be included in this section of VNV results. Next part of the TSR is the ODD definition. We have to clearly state the condition under which the model is expected to perform well. You have to mention that it's valid for UK standard gauge railways and what kind of train types it should be. Train, freight, you can even include the classes, class 66, 67, 68. You have to include the details about the wheel types and wheel suppliers, which wheel manufacturers. You can include in this ODD definition, and also the seasons, which season data was it trained on. Also the track condition, and also you have to include the condition where the system will become invalid, where your verification and validation process will become invalid. So if there is a different supplier for the wheels, or if there is extreme weather conditions, you cannot rely on this system during that conditions. Next section of TSR is monitoring plan. In our monitoring plan, we have to include that how we can detect and respond the problem. There will be like a weekly accuracy tracking. We have to measure the sensitivity and false positive rate on the recent data. And we have to design a system where if the accuracy drops more than 2% from the baseline, the system will go into fallback visual inspection or manual overview of the result. And also we have to do a monthly check where we will investigate the high impact false positive or false negative results. And also if the accuracy drops greater than 5%, or if the new wheel types are introduced, the training has to be retriggered. The retraining of the model has to be done on the new conditions. This is about the monitoring plan. Next section of our technical safety report is restriction. Section 7. That's where we have to include the condition of the deployment. Can mention that this system it can only be deployed on UK freight network, and to do the continuous monitoring, and you have to do you have to retain the manual wheel inspection as a secondary check as our fallback, and then you have to train maintainers for AI interpretation. And all the discrepancies between AI and the actual outcome, maintainer has to provide it to the engineering team. The last section is the configuration control. This is where you have to include about the version and change management. Which model are you using? About your software version, model 1.5, 1.2. Like you have to include the model version. You have to include that training data set. Which data version did you use for the training? Monitoring software version you have to include. Any change in the model will require revalidation. It will require risk assessment. It will require safety case update and also approval before deployment. TSR is typically, it's a long document. It's a very long detailed document, sometimes more than 50 pages, but it's an evidence backing the safety claim. So regulators may review it to assess whether the safety case is justified or not. Okay, now the key insights. These three standards are complementary and interconnected. I'm talking about EN 50126, EN 50128, and EN 50129. So EN 50126, it sets up the assurance framework. It demands from us to identify all hazards, assess all the risks, and define and verify controls. So this practice will produce hazard log and a set of safety requirements. Then comes EN 50128. It specifies the development process to implement these safety requirements. So we will take requirements from EN 50126, and then we will develop the AI system to those requirements. We will verify that the system meets its requirement through testing, and also we will validate that it solves the real world problem. That will be through operation trial. And then as a result, we will produce the evidence, and that evidence will include the test results, your validation data, and operational experience. Then comes the next standard, EN 50129. EN 50129 defines a structure of safety case that synthesizes and argues about the results. So it will take the evidence from our previous standard, EN 50128. It will take the hazard log from our EN 50126. It will build a logical argument, something that says, given the evidence, these hazards are controlled to this cell and the system is safe. So this produces a safety case and technical safety report. So this whole workflow can be divided into 9 stages. First stage is where we will have the hazard analysis and risk analysis that will identify the hazard. So in our case, our identified hazard was that AI model was missing wheel degradation. So second stage is about the risk assessment, where we have to do the risk assessment and assign a cell level. So here we have assigned cell level 3 for this our example. And the next stage is safety requirement. We have to make sure that the model must achieve 95% and above sensitivity. Then fourth stage will be about the requirement, where we will actually design the AI model. Fifth stage about the implementation, where we will train the model. Sixth stage is about verification, where we will do the testing and we make sure that the achieved result is above 95% sensitivity. And seventh stage is about the field trial, that is the validation. So validation is the field trial when the model is in the operational for 12 weeks in depot. During that phase, 95% and above real world sensitivity target was achieved. The eighth stage is about building a safety case. So safety case can be like we have to make sure that the hazard is controlled because model meets its requirement. Then the last stage is about compilation of all your evidence and the supporting data in this case, and then document it in the form of technical safety report, TSR. This integrated workflow ensures that the assurance is systematic, traceable, and defensible. So while EN 50126, 128, and 129 do not explicitly mention about AI, but the modern interpretation using 50127 and RSSB or ISO standards that makes it clear that what must be added to the traditional framework. So let's discuss one by one. So in EN 50126, that is about hazard analysis, risk assessment, and RAMS. We have to include about the definition of ODD clearly. You have to include that under what condition is the AI expected to perform well, and outside those conditions, you cannot rely on the model. You also have to include about the model drift detection. You have to plan how you will detect when the real world condition will diverge from the training condition. What will be the monitoring metrics and what will be the threshold to trigger the actions. Also, you have to include about the retraining procedure. So if the model will drift, how will you retrain it and how often will you retrain it? And what's the procedure for validating or retraining a model before the deployment again? So these things should be added into your 50126 standard, where we are working on hazard analysis, risk assessment, and RAMS. Now about EN 50128, that covers the software deployment. We have to include 3 sections here as well. First one is the data quality requirement. You have to treat training data and operational data as safety critical artifact. So you have to specify data quality standards based on its completeness, its accuracy, absence of bias, and its diversity. Also, you have to include the training procedures and reproducibility. You have to enable the reproduction of training results and document exactly how the model is trained, and then use fixed random seed. You have to version all dependencies, like if you are building it in Python or TensorFlow, everything should be included. Next is something that has to be included in EN 50128 for software development is about the model versioning and configuration control. So each model version is a configuration item. So versioning must be very strict. Any model updates should go through the change control procedure. Next is about EN 50129, that is about the safety case. We have to include about the model limitation and its ODD. The safety case must explicitly state what the model can do and what it cannot do. You must define the ODD and the strict restrictions in the clear words, like it's valid for X and invalid for Y, something like that. Also, you have to include the evidence of training data quality. You have to document the training data about its source, its volume, its diversity, and how representative is it of the real world condition. Then you have to include the monitoring and drift management plan in your safety case in EN 50129. You have to describe how you will monitor the model performance in operations, what will be the KPIs, what will trigger the retraining, and what will be the rollback procedure. So all these procedures you have to include in your safety case. So these additions are critical because they elevate AI from being just another software component to being a well-governed, continuously monitored, and explicitly limited tool within the broader railway assurance framework. Okay, let me summarize the key takeaways from today's session. First, RAMS is integrated. We discussed that reliability, availability, maintainability, and safety are not separate concerns. They are interconnected. You balance them through systematic approach with safety as the overriding constraint. And EN 50126 provides that process. Secondly, then we discussed about EN 50126 that defines the RAMS life cycle. We discussed about 10-phase process from concept through decommissioning. Each phase has its specific activities and decision gates. So critically, the process is iterative. As you learn more, you refine hazard assessment and risk mitigation. So this iterative risk-driven approach is particularly suited for AI where uncertainties are high. Then thirdly, we discussed about 50128, which is updated to 50716, that governs software development principles. So for AI systems, you must rigorously specify requirements about its accuracy targets, about ODD. You must design the model, implement the version control, and verify and validate it comprehensively. Then we discussed about 50129 structures. That's about the safety case. You must synthesize your evidence into logical argument. Given this evidence, this hazard is controlled in this cell level and the system is safe. So, and then we discuss about the technical safety reports as the supporting document for this argument. And we discussed about different sections of safety case first and then technical safety reports. Then we discussed about AI requires explicit extension to the traditional standard framework. You must define the operational design domain, ODD. You must implement continuous monitoring for drift and out of ODD operations. You must manage model versioning and training as a safety critical activities. You must ensure that the data quality is governed like software code. And then you have to build explainability and transparency into the system design so the operator understands the model's capability and its limitations. So these standards 50126, 128, and 129 are not obsolete in the age of AI. They are more important than ever because they provide the disciplined, systematic approach that AI systems need to be safe, reliable, and trustworthy in critical infrastructure environment like railways.
All right, that's it for this session. If you found this helpful, hit the subscribe button and turn on notifications so you don't miss the next one. And quick reminder, make sure you check out the podcast series here on the channel, RAMS Ready for Everything RAMS, and Safe Tracks for System Safety Assurance. If you're following along with this course, those episodes will really help connect the dots. Thanks for watching and stay tuned for the next one.